In this section, we're still looking at roots, zeros, or solutions of polynomial expressions, but today we're going to be looking at a couple different ways to find these. So when we're talking about the zeros, roots, or solutions of a polynomial expressions, basically we were looking to figure out what values of x make it a true statement. So not even having the function, but just looking at a picture, this particular graph shows me very distinctly that I have the solution here, here, and here. So this is a third degree polynomial. So this graph is some sort of an x cubed function, x cubed plus some other terms, some x squared, some x's, and maybe a constant. But these are my solutions. So again, these are called the roots, the zeros, or the solutions. They all mean the same thing. They're all interchangeable. Now, why do we call them this? Because if I set my function equal to 0, these are the values of x that will produce 0 for my y value. So again, it's when x values cross, the values where x crosses the x-axis, or my x values where that crosses the x-axis, or my roots, my zeros, and my solutions. I don't care where it crosses the y-axis, because that's where our value of y is equal to some other value, let's say like -2 in this case. We want to know where y equals 0. And y equals 0 wherever it crosses the x-axis. So what we're going to be looking at today then are some different ways of solving or finding these. The first question that we'll run into in our homework set asks you to consider a polynomial expression. Now when we talk about a polynomial expression, we're actually referring to powers. So we're talking about x cubed, x to the 4th, x to the 50th. So polynomial expression. Now notice we don't have any fractions in our powers, and we don't have any square roots or anything else running along here. Our coefficients could be fractions, or coefficients could be square roots, but none of my powers are. So it says consider the polynomial function with integer coefficients. So a sub n is a coefficient, a sub n minus 1, a sub 1, a naught. Those are all called our coefficients. So these are the a sub n's. Now our powers are up here in the exponent. So this is an nth degree polynomial. So it could be a 5, it could be an x to the 5th, it could be an x to the 10th. And this is just saying basically I have a coefficient and I have decreasing powers of x. And this says that my leading coefficient, a sub n, which is right here, can't be 0, which makes sense because if it was 0, we wouldn't have this term at all. Now it says the rational zero theorem. Okay, so the rational zero theorem is basically giving me a starting point to try and find solutions. And they're basically saying that the rational zero theorem states that if p over q is a rational zero, where p over q is reduced to lowest terms, then p is a factor of, now this is going to be a naught. And then q is a factor of a sub n. Now I'll explain what this means in just a minute. So a naught is our last term divided by my first term. So p over q is the last term, and it's usually a constant, over my first term, and again it has to be in order from highest to lowest powers first. And then basically what this is doing, it's giving you a lot of different options for finding roots or coefficients or solutions. So a naught over a sub n, last term over first term once the terms are ordered. So let's look at an example of where we're asked to actually come up with this list when numbers are involved. When we're just looking at variables and these a naughts, etc., it's kind of hard to find some of those solutions. So on our homework problem that we have next, it says determine whether the following statement is true or false. And they want to give me a problem where I'm asked to find out potential solutions. And so that's what we're up here for. We're saying, okay, what are some potential solutions? And here they call it possible rational zeros. Okay, well, let's not worry about this number right now. Let's go ahead and list all possible rational zeros. Because a lot of problems you have to actually list them all. Okay, so remember, these are ordered 3, 2, 1 constant. So it's always the last divided by the first. Okay, so the last is a 3. So I could have a positive or negative 3 or a positive or negative 1, because it's not just the last or first term, it's the factors. Okay, now my first term would be this 8. Okay, so that would be plus or minus 8, plus or minus 1, plus or minus 2, plus or minus 4. So these are all the numbers that don't go into 8 evenly. Now, list all possible rational zeros means to actually list out all of these possible ratios. So I'd have plus or minus 3. Yeah, I think I'll start with the 1 first, just to stay in order here, order from smallest to largest. So plus or minus 1 over plus or minus 8. Plus or minus 1 over plus or minus 2, and that's coming from here. Plus or minus 1 over plus or minus 4, and plus or minus 1 over plus or minus 1. Okay, so there's a partial list. Now the rest of this will come from the plus or minus 3 that's in the numerator. Plus or minus 3, plus or minus 8, plus or minus 3, plus or minus 2, plus or minus 3, plus or minus 4, and then my last one, plus or minus 3 over plus or minus 1. Now I have to reduce these. Okay, now 1/8 is already reduced, 1/2, 1/4. Now this plus or minus 1 over plus or minus 1, that's actually just going to be plus or minus 1. 3/8 is reduced, 3/2, 3/4, and 3 over 1. So if I had to make a complete listing of all possible values, plus or minus 1 over plus or minus 8 could be a negative 1/8 or a positive 1/8. So I'm going to say plus or minus 1/8. Okay, so this one's done. This would be plus or minus 1/2, plus or minus 1/4, plus or minus 1, because 1 divided by 1 is 1, plus or minus 3/8, plus or minus 3/2, plus or minus 3/4. And then our last one, 3 divided by 1 is 3, so it's just plus or minus 3. So these are all the potential or possible roots where it would cross the x-axis. And so it's giving me a list that's smaller than every single possible number, and it's saying, you know what, you could try some of these to figure out what our roots are. So it's saying, is 4/3 a possible rational root? And if we look at this, and we're looking for our ratios for 4/3, I would have to say it's not listed. Now you can see over here I have a 3/4 in the other direction where the 4 is in the denominator, but again it has to be the last factor divided by one of the first factors. So this would be false. It's not on my list. Now if you're asked to make a complete list like this in my math lab, you have to separate the plus and the minus. You'd have to write negative 1/8, comma, positive 1/8, etc. So this is a long list. This is a lot of numbers. So when you're asked to find these lists, remember it's always the last factor list divided by the first factor list, and then all possibilities. Let's go ahead and look at another example where we're asked to find whether we have a root, a potential root. Now both of the questions that we've looked at or will be looking at so far is just asking about, is it a possible root? It's not asking for an exact root, it's just saying, is it a possible root? So let's look at our next one. And this one's going to be a little bit smaller list, which is nice. So here we have, determine whether the following statement is true or false. The value of 1/5 is a possible rational zero. It doesn't mean that it is a rational zero, it just means does it has the possibility of being a rational zero by using the rational zero theorem. Okay, so let's go ahead and list all possible rational zeros. Okay, remember it's last over first. So last over first. So if we look at our last term, that's just plus or minus 1, and you might say, well, wait a minute, why do you have a minus 1 when there's a plus sign out front? Because this could be minus and negative, which is the same as this positive, so I have to look at all possible factorings here. Now for 9, I can have plus or minus 1, plus or minus 9, and plus or minus 3 times 3 is 9. So if I made my entire list, it would be plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 3, plus or minus 1 over plus or minus 9. And again, if we had to write these out, we always reduce them. 1 divided by 1 is 1. 1/3 does not reduce, but I still have the positive and negative, and 1/9 does not reduce either. So this is the list of all possible rational zeros. And if you look, 1/5 is not part of this list, so I would say that it's false. 1/5 is not a possible rational zero here. So these aren't too bad when you get started. They try and give you some hints about the number of possible rational zeros. They give you a list usually to choose from, a multiple choice list, as opposed to having to write out all the possibilities. But sometimes you will run into an example where you will need to write out the possibilities, and if you do, remember you have to separate the negative and the positives. Now, we talked about the rational zero theorem, and we talked about a graph toward the beginning here, but what we haven't talked about are how many possible roots are there going to be. So let's look at some examples. Let's say we have linear polynomial. Okay, so this would be something like y equal 2x plus 3. Well, if we had an equation that was linear, the most number of times that this can cross the x-axis or have a root, a solution, or a zero is once. Now we can also get a linear to cross only once. We can't get it to cross twice because it would have to turn back down. I can get it so it doesn't cross at all if it is a horizontal line. So this would be 0 roots up here. And another way to say roots is a 0. Here we have a single root, or a single zero, or a single solution. So if you think about it, the power on my linear term is 1, and the most number of roots is 1. Let's go ahead and look at quadratic. Now if we think about a quadratic, there's several different options here. I could touch the graph twice, whether it's opening up or down. But I can't ever get it to touch 3 times as it crosses the x-axis, because remember, we're only interested in the x-axis. It could touch once, it could touch and turn, and here I'd only have 1 root. Or it could be the case where it never touches the x-axis at all and I have 0 roots, I have 0 solutions. So here I have 2 solutions, 1 solution. Now remember, solution, zeros, and roots all mean the same thing. And here I have 0 solutions. So the highest power on a quadratic would be something, let's say y equal x squared. The highest power is a 2, and the highest number of roots that is possible is a 2. It could actually go down to 1 and 0 as well. If you count the number of solutions here, it only says 1 solution, but what happens when we would work a problem like this is we would have a double root. I'd get the same solution twice. Let's go ahead and look at a third degree polynomial. So for a third degree polynomial, I could have the example where I touch once, and I can't think of an example where you would touch 0 times with a third degree polynomial. I can think of an example where we would touch twice, so I would cross and then I would touch and turn. So here I'd cross and touch and turn, so I have 2 solutions. And then I have that third case, the third degree polynomial, so the most number of roots I can have is 3, where I would cross the x-axis 3 times. So this is 1 solution, this is 2 solutions, and this is 3 solutions. These are my possibilities. Now when we're working this type of problem again, I don't think we can take this odd power, this odd degree, and get it to touch 0 times, because of the nature that it's moving from negative to positive infinity. So again, the highest degree here, y equal x cubed, let's say, third power, highest number of solutions is 3, and of course I can get lower solutions as well if I double count these roots. Let's go ahead and look at a fourth degree. Now a fourth degree polynomial can look like a lot of different things. As we go up higher and higher in powers, it's kind of difficult to draw all the possibilities, but I think you can see the trend here. A fourth degree polynomial sometimes can look like a W shape. Now it can also look like a W shape where we touch and turn. It could also look like a very, very wide parabola. It could touch and turn once in a very wide parabola fashion. And all the examples I'm drawing here are opening up, but it doesn't have to just open up. It could also open down and never touch or cross at all. So we can see here a fourth degree polynomial, 4 powers. The most number of times I can get this to cross the x-axis is 4 times. So here I have 4 solutions. Here I have 3. Here I have 2. Here I have 1 solution. And here I have 0 solutions. So again, this is 4 solutions, 3 solutions, and again these could be called roots or zeros as well, 2 solutions, 1 solution, and 0 solutions. And we could keep going on and on with the 5th degree, the 6th degree, etc. But I think you get the general idea. So way back up here in the problem that we were given, it says if a polynomial is of degree n, that means its highest power is n. In this case, n would be 1. Over here, n would be 2. Over here, n would be 3. Then the counting multiple roots separately, the equation has n roots. So we're going to be looking at the number of roots that it has. It could have up to n roots. Now again, for where we have 1 solution here, this is actually a double counted root, so it does have 2 solutions. They just happen to be the same. So that's when it means when it's counting multiple roots. So now we can start talking about how we actually find these roots from the list of all possible roots that we can find using that very first theorem that we looked at, the rational zero theorem. Now some of these can get pretty long, so I think it's probably a good idea to start thinking about and talking about using your calculators to help you narrow down all the possibilities. So what does it mean to be a root, or to be a solution, or to be a zero of a function? Well, basically that means when we divide, we end up with 0 as a remainder. So again, this is our remainder. Now when we start with our highest powers, I always like to sketch these in. This was 4x cubed, this was x squared, this was x, and this is our constant. So when I get done, I go down a power. So now this is x squared, this is constant x, this is constant, and this is my remainder. Because there is a remainder here, that means that -4 is my root. That also implies if -4 is a root, then I know that x plus 4, the opposite, is a factor. Okay, so this factors, one of the factors of this expression is going to be x plus 4. So the next part to this question will be, what is the remaining factor? So I know my original was 4x cubed plus 15x squared minus 5x minus 4 equals 0. And I just found out that x plus 4 is a factor. My remaining factor comes from right here going down by my powers. So I have 4x squared minus 1x, I just put in my minus x, and minus 1 for my constant equals 0. Now this 4x squared minus x minus 1 does not factor any further, so I'm done. I can't find any more solutions from this. Our solutions here would be complex numbers. So if we have to keep going and factoring with this, I'm done. But this is how this third degree polynomial factors. This piece will give me a solution or a root of -4. This piece does not give me any solutions at all. Now if we were to graph this, let's see what it would look like. So we'd have 4x cubed plus 15x squared. So we'd hit the y equal key. So 4x cubed plus 15x squared minus 5x minus 4. Now we might have to adjust our window here a little bit, but I know something's going on at -4 because we already caught that from our original problem. So it looks like it's crossing here, and then I'm crossing here and here as well. So it's having 3 roots, but the other roots I can't find as integers. They're going to be fractional values. So I'd probably have to use the quadratic formula or something like that from here. Let's go ahead and go to window. It looks like on my Y max I need to go way up. And again, you can choose any values that you want here. I'm just going to go up to 50. Maybe we can get a better look at our graph. Oh, there it goes. 1, 2, 3. So here's our -4, and then I know I have a root between 0 and -1, and another root between 0 and 1. So what we found then was our one integer root. There's other ones out there, but they don't factor nicely, so I'd have to use a quadratic formula to come up with those. Now if I want to find those exact values, I can go to my calculator, find second, math, and under math I hit the 0 option to come up with the decimal approximations. So here's my solutions, 1, 2, 3 solutions, and this is my root of -4. These other roots I'd have to find with quadratic formula or completing the square as well. But the most important thing to come out away with this problem was, if it's a root, when I use synthetic division, the remainder is 0. Now some of the problems that you're going to be finding just basically say use the rational zero theorem and list all possible rational zeros. They don't ask you to actually find any rational zeros, they just say find all the possible rational zeros. So I don't think with those problems you'll have much trouble. I want to focus more in on the problems where they give you an idea of a solution, and then based on that start they want you to find more solutions. Now you have to be careful with these problems because there's a lot of different possibilities, and so they can get a little bit long and make it easy to kind of give up on them, but I would start each one of these problems by graphing so I can kind of have an idea of what I'm looking for. Okay, so for this problem we have 2x cubed plus 6x squared plus 5x plus 2. So I'm going to take my own advice and graph this. So I have 2x cubed plus 6x squared, whoops, gotta make sure it's in there, plus 6x squared plus 5x plus 2. Now our scale might be a little crazy on this one because I went up to 50 on my last graph. So it looks like to me I'm crossing once and maybe touching and turning. It's hard to tell, so I want to change my window, and instead of going up to that 50, let's change it to just 10, and let's go down to a -10 on my Y min. So we should be able to get a better idea if that's actually touching or crossing. Okay, oh, it's not even touching at all. So looking at this scale really clarified that I'm only looking for one solution here, because it's only touching the x-axis one time. Okay, so we know before we even start we have one solution, and it looks like to me that that solution is a -2. So first part of this question, it says list all rational zeros that are possible according to the rational zero theorem. Okay, well remember it's last over first. Well, my last term is a 2, so the factors of 2 are plus or minus 1 and plus or minus 2. And my firsts would go after the coefficient that's in front of the highest power, so it would also be plus or minus 1 and plus or minus 2. So if I have to write out all these possibilities, it would be plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 2. Whoops, this should be a 2 right here. So plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 2. Now the second one, the 2 will be my numerator, plus or minus 2 over plus or minus 1, plus or minus 2 over plus or minus 2. Now this reduces to a 1, and this reduces to a 1, so when I make my list I don't need to double count them. So I'm going to have a -2 from here, and then I'll also have a +2 from there. Now from over here I'll have a -1 and a +1. And again, I'm ordering these from smallest to largest. So -1 and +1 are here. Now this 2 over 2 reduces to 1 as well, so that's counted here. And then I have a negative 1/2 and a positive 1/2. So that's my complete list of all of the possible roots or solutions. These aren't all the answers, these are all the possible answers. Okay, so let's go ahead and put that answer in. Again, I ordered these from smallest to largest. It says to type an integer or a simplified fraction, so you wouldn't want to put in something like 5/10. You'd always want to reduce that to 1/2 if you could. Now the second part says use synthetic division to test several possible rational zeros. Well, we have 1, 2, 3, 4, 6 possibilities. So instead of randomly trying to guess which one you should try, I think the best thing is to look at your graph. Now from this graph, it looks like to me that a solution is x equal -2. So the one I would want to try and start with synthetic division is a -2. So the -2 would go out front. And again, you could try 5 different other possibilities before you ever struck on -2 as a solution. So I think it's better to graph it, and then from the graph look at a possibility instead of just trying to randomly trying, because it can get a little bit frustrating. So 2x cubed, so I'd have a 2x cubed plus 6x squared plus 5x plus 2 is my constant. And I always put the powers because it just helps me remember that I need zeros for placeholders. Remember, we bring the 2 down, we multiply up. -2 times 2 is -4. Add down, multiply up. -2 times 2 is -4. 5 minus 4 is 1. -2 times 1 is -2, and my remainder is 0. So let's look to see what happens to my powers. X cubed goes to x squared goes to x goes to constant goes to remainder. So remainder equals 0 implies that -2 is a root. If I had a remainder, let's say I tested the number 3 and I got a remainder, that would say 3 is not a root. So one rational zero of the given function is -2, and I've established that it is -2 because I do not have a remainder here as well. Now I don't have any other rational zeros for this function, but sometimes it will say, okay, now that you know one, go find all the rest. Well, in this particular case, I don't have any other ones to find. So for this problem, when it asks to list all the real zeros, I would be listing just -2 again. So sometimes you'll have a lot of other ones that I'll have to keep trying, but again, if you can graph these, it's going to be so helpful to get started. Now if we look at our other factor here, and it didn't really ask us to list this, but I think I will go ahead and list it. Remember, my original function was 2x cubed plus 6x squared plus 5x plus 2. It came from right up here as our given value up here. So far I've gotten this to factor. I got it to factor into x plus 2, and I know it's x plus 2 is my factor because -2 is my root. And then my remaining factor was 2x squared plus 2x plus 1. Now if I'm trying to find my roots, I can go ahead and set these equal to 0. Now this does not factor into anything that's going to give me an integer response. This is going to factor if I go ahead and use the quadratic formula. I'm guessing it's going to factor into complex roots. And we'll talk about complex roots in a little bit. But for now I want you to keep in mind that at this point you sometimes have to go further to try and get it to factor further. So this one, they give me a list of all possible rational zeros, and I need to choose the one that fits. So this first part lists all possible, not all my solutions, but all possible rational zeros. Remember, that's last over first. My last coefficient is 4, so the factors of 4 are plus or minus 1, plus or minus 4, and then plus or minus 2. The denominator would be the coefficient here, which is just a plus or minus 1. So if I had to list all of these, I'd have plus or minus 1 over plus or minus 1, plus or minus 2 over plus or minus 1, and plus or minus 4 over plus or minus 1. And of course, all of these reduce. Plus or minus 1 over plus or minus 1 is just plus or minus 1. 2 divided by 1 is 2. 4 divided by 1 is 4. And so you can see that D is my correct solution here. So that's our first option. Now, that's just part A. So for our next part of this, it's going to say, okay, those are all the possible solutions. Use synthetic division to test a bunch of these. There's 6 to test, positive and negative 1, positive and negative 2, positive and negative 4. So it says just go through and randomly test a bunch of these until you come up with 0 as a remainder. Well, I think that's very tedious, so I'm going to graph this before I go any further. So let's graph x cubed minus 15x minus 4. And what we want to do is we want to find any nice integer solutions that we can. Okay, so again, it was x cubed, so we'll go ahead and clear out of this. X to the third minus 15x minus 4. Okay, now we might have to adjust the screen, but let's see what we can find out. Okay, 1, 2, 3. It's crossing 3 times. It looks like this one is definitely a fraction or a square root. Same here, but this one looks like an integer solution. So if I can find that integer solution, it's going to save me so much time. Now for my y min and my y max, I'm going to go pretty extreme here. I'm going to go negative 50 to 50, just so I can get a good look at the shape of this graph. Okay, so I see I have 3 roots. One of them definitely looks like it's an integer solution. And of course we can use second calc on our calculators to try and find that. And we'll look to see how we can come up with that value. So on your calculator, you would go second table, and we thought 4 was a root. And we can see pretty clearly here that if x is 4, y is 0, so 4 is definitely my integer solution. I can also see from here that I'm switching from, anytime my y values switch from positive to negative or negative to positive, that means I have a solution. So because my y values are switching from negative to positive, that means one of my answers is between negative 4 and negative 3. And because it's switching back again from positive to negative, I have another solution between negative 1 and 0, which matches up with our graph perfectly. So instead of randomly going through and trying and testing these, let's go after the nice integer solution that we can see from our graph. So this is x equal 4. So one rational solution of the given equation is 4. Well, we still have to use synthetic division to establish that, and then we also need to figure out what the remaining factor is. So again, this was 1x cubed. There was no x squared. There was a minus 15x, and then there was a minus 4 for my constant. So I bring the 1 down, multiply up, add down, multiply up. Negative 15 plus 16 is 1. 4 times 1 is 4. Remainder is 0. So now my powers go down. X cubed becomes x squared becomes x becomes constant, and my remainder is a 0. So remainder equals 0, therefore x equals 4 is a root, or a solution, or a 0. So again, this is what we have going on. We had x cubed minus 15x minus 4 equals 0. So when you're using the quadratic formula, identify your values of a, b, and c right away. So in this case, a is equal to 1, b is equal to 4, and c is equal to 1. Again, that's a, b, and c. Then we go ahead and write out the quadratic formula. Now whenever you're using the quadratic formula, it's always a good idea to put everything inside parentheses so you don't accidentally drop a negative value or don't treat a negative value correctly. Now in this case, we don't have any negative values for our coefficients of a, b, and c, but it's still a good idea to put them in parentheses. So we have x equal negative 4 plus or minus. Now in parentheses I have 4 squared, which is 16. 4 times 1 times 1 is 4, and I'm subtracting, and this is all over 2. Now the 2 does not cancel into the 4, because it also goes underneath this radical. So the square root of 12 can break up into root 4, root 3, square root of 4 is 2. And now I can actually start factoring out. So here I have negative, let's just go ahead and pull out a 2. If I pull a 2 away from here, I'm left with negative 2 plus or minus the square root of 3 all over 2. Now the 2's cancel. So I'm left with two solutions, negative 2 minus root 3 and a negative 2 plus root 3. Well, let's go ahead and look at a decimal approximation for negative 2 minus root 3. So let's do negative 2 minus square root of 3. Shouldn't have erased that graph. We might have wanted to look at it again. So here I got the negative 3.73. Now if you remember from our table that we looked at before, one of our values was between a negative 4 and a negative 3. So this seems to agree with that or to support that solution. Our other one, negative 2 plus root 3, let's go ahead and find a decimal approximation, negative 2 plus square root of 3. And remember, you can check your answers like these even if there's decimal or square roots. Now this seems to support our other solution, which was between 0 and negative 1. So even though we can't come up with an exact answer, you know, we can't look at a square root value in our calculators, we can still come up with these nice approximations. Okay, so let's see if these match. I foolishly erased our graph, which was x cubed, x to the third, minus 15x minus 4. Okay, so we found this one already. The one I think we found was between 0 and negative 1 is here, and between negative 3 and negative 4 is here. Now if I want to find out exactly what they are, I go second calc, choose my 0, and I'm going to do left bound. Let's go clear to the leftmost 0. Right bound, and just hit enter one more time, and here it is, negative 3.732051. And let's see if that agrees with what we had for that problem. Now you can do the same as well for the other 0. I'm just going to do it for one of these to show you how to do it, and then I'll leave it up to you to actually try that. These always come in way oversized. So it looks like this negative 3.73205 is this point right here. That matches exactly minus 2 minus square root of 3. This approximation matches this one over here. So you can check your answers even though your solution is in terms of a square root. You can check with a decimal approximation. Now the last problem that we're going to look at comes up with the idea of using complex numbers. Those are, remember, like I, a plus bi, negative 3 plus 2i types of solutions. So we're looking at getting complex solutions. So when we talk about complex solutions, we would get to a point where we factor, we find a root, and then what the remaining trinomial is, let's say, doesn't factor using the quadratic formula. I get a negative value under the square root sign. Now the thing that we want to remember would be this. Complex solutions come in conjugate pairs. So let's go ahead and talk about what that means. So that means if we know, let's say that I is a solution, I could write that as 0 plus I. The conjugate pair to that would be 0 minus I. So let's look at another example. Let's say 4i is a solution. So in standard form that would be 0 plus 4i. That tells me that the conjugate pair is 0 minus 4i. So we have to be careful about how we're working with these. 0 plus I, 0 minus I, these are called our conjugate pairs. So I don't have to be given both of these in order to come up with are solutions. I just have to be given one of them. And once I come up with the second one, then I can start talking about factors. So let's go ahead and look at the idea of conjugate pairs, how that relates as a root to a factor. Well, in this particular case, if plus I is a root, that would mean the factor that it came from was x minus I. Over here, if negative I is a root, x plus I would be the factor that it came from. Same thing here. X minus 4i was the factor that the root 4i came from. X plus 4i is the factor that the root negative 4i came from. So we're going to be looking at some problems that basically have conjugate pairs. I have solutions that are complex numbers, and I'm not going to be given the original function, which is kind of backward. It kind of seems like, man, I should be given the original function to work with here. We're going to be given the roots and asked to work backward. So this is one of the harder problems that you'll see in this homework set, and I'm going to walk you through an example step by step. Okay, so it says find an nth degree polynomial. Well, in this case, n is 4. So what that tells me when I get done, I might have a coefficient here, and then I'm going to have an x to the 4th plus other stuff going on. So it's a 4th degree polynomial. My zeros are I and 3i. Okay, so my roots are I, and of course because they come in conjugate pairs, I know I have a negative I, and I also tell me that I have 3i as a root, so that tells me I have a negative 3i over here because I have a conjugate pair. And then this f of negative 1 equal 20, I'm going to use that toward the end. So because I don't have any real roots here, to me this looks like it's not going to ever cross the x-axis. So this is going to be a 4th degree polynomial. It's going to look like a very, very wide parabola. Might have a little bit of a twist or a turn in it, and it'll either be opening up or down. I don't really know yet. So to get started, I could talk about fn of x. Now this n just means my nth degree polynomial. And this a sub n is this coefficient. I don't know what it is yet. However, I do know my factors are x minus I and x plus I. And again, if these are my roots, then the factor is x minus I, x plus I, because they're always opposites. X minus 3i, x plus 3i. So I have x minus I, x plus I, x minus 3i, x plus 3i. Now, this is worse than it looks. The a sub n we just pull out front. Now I'm going to go ahead and FOIL this out. X times x is x squared. Now the cool thing about conjugates is when you multiply your outsides and your inside terms together, they cancel out. So here's plus ix minus ix, and then negative times a positive is a negative I squared. X times x is x squared plus 3xi minus 3xi. And again, because I multiply by conjugates, the outside and the inside terms cancel. Negative 3 times a positive 3 is a negative 9. I times I is I squared. So outside insides cancel. That will always happen with your conjugates. So let's see what we have left here. I have x squared. Now remember, I squared is a negative 1. So this is minus a negative 1, which is the same as plus 1. Then over here I have x squared, negative 9. I squared is a negative 1. Negative times a negative is a positive. Okay, so now we're given a little bit more information. We are also given way up here that f of negative 1 equal 20. So we know that f of negative 1 equal 20. Okay, so over here on this side, here's my f of x or fn of x, either way. So I know over here f of negative 1 equals a sub n. Now in place of this x squared, I would plug my negative 1 then. Negative 1 quantity squared plus 1. Then over here, in place of this x, I plug in a -1 as well. Make sure you use those parentheses, otherwise your negative squared might end up to be positive. And when I get all done, I know this has to equal 20. So let's see what we have here. So I have my a sub n out front. -1 times -1 is 1. 1 plus 1 is 2. -1 times -1 is 1. 1 plus 9 is 10. Equals 20. So over here on this side, 2 times 10 is 20. So I get 20 times a sub n equals 20. Divide both sides through by 20 to solve, and I get a sub n equal 1. Well, we've done so much work here, you would think that we'd be done, but we're not really quite done yet. What I need to do is I need to take this value of a sub n, I need to plug it in right here. So I have f of x equals 1 times x squared plus 1 times x squared plus 9. Now in the problem that you get in your homework set, I was lucky and I just got a number 1 here, but you could have a 2, a 3, a -1/2. And now what I need to do is I need to actually write out the polynomial expression. So if this was a 2, I would FOIL this out and distribute the 2, but since it's just a nice little 1, I can just drop it, and I FOIL this out and I get x to the 4th plus 9x squared plus x squared plus 9. And again, if this was a 2 or something out front, I'd multiply it through, but I'm going to go ahead and combine my like terms. X to the 4th plus 10x squared plus 9. Now this is the final solution. Now if I tried to find the answers to this problem, what would happen is I would not get this to cross the x-axis. I would come up with just 4 complex solutions. It would never cross the x-axis. So we're already using up quite a bit of time here for this lecture, but let's go ahead and graph x to the 4th plus 10x squared plus 9. So let's clear this out. X to the 4th. It shouldn't cross the x-axis because I should have complex solutions. So I have x to the 4th plus 10x squared plus 9. It's nice to be able to kind of check your intermediate work here. Let's hit graph. Might have to adjust our window. Yep, there it is, that nice wide parabola. It's not crossing the x-axis, so I don't have any real solutions. I only have complex solutions. So our graph verifies that. So definitely one of the harder problems. It's long, but it's definitely doable because you have all the skills that you need. Let's go ahead and look at our very last problem that you'll see in the homework set. This is an application problem, and it looks a little bit more difficult than it is, but let's go ahead and start by setting it up. We have a solid that's given to us with some dimensions. It says if the volume of the solid shown in this figure is 648 cubic inches, find the value of x. This problem looks a little bit harder than it is. If we just think about finding the volume of the overall cube, I guess it's not going to be a cube, it'll be a rectangular solid, and then just cutting out this section in the middle. So let's go ahead and start with the idea of the volume. The formula for volume is length times width times height. So if we wanted to, we could call this the length, x plus 3. The width is out front, would be this 3x plus 1. And then the height is over here on this side, x plus 1. Well, that's if I was finding the volume of the entire piece, but I need to subtract out this section right in here that goes all the way to the back. So let's go ahead and find the volume of that piece, and then we'll section that out. Well, the volume of that piece is going to be the length, and the length right here should match x plus 3. The width is this value of x, and the height is 3. So this is where I'm going to get started, and they tell me that the volume is 648. So what you're going to do is multiply these out, combine like terms, and then hopefully we get to a point where it's factorable. But again, if I were you, what I would do is right away I would subtract this 648 over and graph this, and then get an idea of what your possible solution could be. So what you would graph then is x plus 3, 3x plus 1, and you don't even need to multiply these out. And then you have to subtract over that 648 though to get it set equal to 0. So this is still your formula for volume, but you would graph this, and then based on this adjust your screen size and kind of look through there and see where is it crossing the x-axis. Is it crossing at an integer value? Is it crossing at a decimal that I can convert to a fraction? If you don't like the idea of graphing, you're going to have to expand, combine like terms, and then solve using one of the ideas that we've learned, synthetic division, looking at all the possible rational zeros. Good luck on this assignment. It's not too hard. Some of the last problems are a little bit more difficult, but I think you have a good template to work with. As usual, if you have questions, let me know. Bring your questions to class. You can stop by my office, or the Math Center is open as well. Good luck.